Okay, this is the lesson video for AP Calculus AB, and this is section 3.2, where we discuss the idea of differentiability. And what I want to tell you here is in this video, this is largely going to be conceptual. You will have a lot of problems in your homework that won't be as much focused on the conceptual ideas, but what I want to focus on are the main ideas that are in this section. And then in addition to that, we're going to start doing derivatives with your calculator today. So if you do have a calculator available to you, it would be a good idea to have that out while we go through this lesson. So to start with, the whole idea of differentiability we discussed briefly in section 3.1. And differentiability just means that if I take the derivative of a function, it exists. So if I say a function is differentiable at a point, that means the derivative exists at that point. Now remember, a derivative is a limit. So in order for the function to be differentiable, the left-hand derivative has to equal the right-hand derivative. The other part of differentiability is that in order for a function to be differentiable, it also needs to be continuous. So all continuous functions are not differentiable, but all differentiable functions are continuous. And that's what this statement here is basically saying, is that if a function is differentiable, then it's definitely going to be continuous. It doesn't necessarily work the other way around. Okay, so let's take a look at some situations where the derivative fails to exist graphically. And you can see on the first one that we have here, it's referred to as a corner. And this is the absolute value of x. You can see at this point, at x is 0, this function would not be differentiable because the right-hand derivative would be 1, because on the right side we have essentially a linear function with a slope of 1, and the left-hand derivative would be -1. So since the one-sided derivatives don't match up, that means the function is not differentiable. Same idea over here when we're looking at a cusp. So as we approach x equals 0 from the right, you can see that our slope is getting steeper and steeper. And what's happening there is if we approach from the right, we actually have an infinite slope. And then as we approach from the left, as we come from this side, we have a slope that is approaching negative infinity. So we have that instantaneous switch from a very, very steep negative slope to a very, very steep positive slope. And again, the left and right-hand derivatives aren't matching up, so the function's not differentiable. For a vertical tangent, it's just as it's described here. If I were to draw in a tangent line here, you can see that tangent line is completely vertical. The slope of a vertical line is undefined, so the derivative would be undefined, so that means it's not differentiable at 0. And then the last one is just when we have a discontinuity. And so this really comes into play when you start trying to solve out your one-sided derivatives using the definition of derivative. Since you have this point that doesn't match up with this section of the function, when you get that left side derivative, it's going to come up as being undefined as you approach 0 from the left. So with that being the case, again, the function will not be differentiable at that point. So those are the 4 cases that we would be looking at: a corner, a cusp, a vertical tangent, or a discontinuity. Those are all places where the function is not differentiable. Okay, so I'm going to show you some things on the calculator here in a few minutes, but just to make this a little bit easier, I've got some graphs here to give you a better view of what's happening graphically when a function is differentiable. So we're looking at this whole idea of local linearity. And what that means is, if I zoom in on a point enough, eventually I should be able to see how that point looks essentially linear, or the graph sort of has linear behavior about that point if it's going to be differentiable. So this is the absolute value of x plus 1. And here's the first view of the graph. We can see this is kind of the standard view. If you graph this on the calculator, you can see it looks like it has that V shape. As I zoom in here, you can see this is zoomed in a little bit more. And then here we've got a third graph that's zoomed in even a little more. And then a fourth graph that's zoomed in even more than that. No matter how much I zoom in, I'm seeing that instantaneous switch from a slope of -1 on the left and +1 on the right. So I'm always going to hit that sharp turn in my graph, which is indicating to me that this function's not going to be differentiable at that point. Okay, so here's another example of a graph that looks similar to that actually is differentiable at 0. So we have this function, square root of x squared plus 0.0001, and that quantity is plus 0.99. So notice the graph here. When I graph it on sort of a standard window, it looks like we have an instantaneous rate of change, or excuse me, an instantaneous change from a negative slope to a positive slope at 0. So it looks like this function may not be differentiable at 0. But now I'm going to go through these graphs, and I'm going to show you as we zoom in on this graph, you're going to start to see that this function actually doesn't have a point where it's not differentiable. Now you can see on this graph how it's sort of starting to have like almost like a quadratic behavior about x equals 0. And when I zoom in enough, you can start to see that it actually has a horizontal tangent here. And that's what the idea of local linearity is if I zoom in on that enough, it starts to resemble some sort of a linear tangent line function when I get really, really close to one of these points. And we can keep zooming in on this, and eventually, if we zoomed in enough, it would just look like a horizontal line at x is 0, indicating that we do have a tangent slope. So be careful when you look at these things on the calculator. That's one of the themes today, is that the calculator can be kind of misleading. So it's not just necessarily looking at the graph on the calculator, it's also understanding what's happening with that graph, because like you saw in the last one, if we didn't zoom in on that graph, you would think the function's not differentiable when it actually is. Okay, so let's talk a little bit about differentiability of piecewise functions, and then we'll get into a little bit of work with the calculator. So when we talk about the differentiability for a piecewise function, that's where we're talking about a function that has different rules for different domain sections of your function. There's two things that have to be true in order for a function to be differentiable. And really, this has to be true everywhere. It's not just for a piecewise function. We always need to check, is the function continuous? And we always need to check, does the right-hand derivative equal the left-hand derivative? Well, for a piecewise function, that's a little more difficult to do, but it's still kind of the same idea. So what I'm going to do here is I'm just going to go through those two steps. So this is what it said up above for the first thing that we check is continuity. Well, if I'm checking continuity using this piecewise function, so this function is linear to the left of 1, has a slope of 1, and then it's quadratic to the right of 1. Well, if I look at f of 1, that's equal to 1, and if I took the limit as x approaches 1, you would see that for both of those rules, I'm going to get a value that's equal to 1. Okay, so that is basically justifying that this is a continuous function. So I've shown continuity by showing that the limit value is equal to the function value. Okay, so it's continuous, but now let's look at the second part of this. When I look at the second piece of this, what I would have to do is I would have to write a derivative function, a piecewise derivative function. And for that first rule for x, just think about the slope of a line. It's constant. X has a slope of 1, so that my derivative value is always equal to 1. And that's for x less than or equal to 1. If we were to find the right-hand derivative, or the right side derivative, or the derivative of the second piece of the function, if you want to call it that, we can use the definition of a derivative, and we've seen this one several times now. The derivative would be 2x, and that would apply where x is greater than 1. Now, for differentiability at x is equal to 1, what we need to see happen is that we need to see the left-hand derivative equal to the right-hand derivative. So this rule should be giving me the same thing as this rule when x is equal to 1. And you can see that the left-hand derivative is actually going to be 1, where the right-hand derivative is approaching a value of 2. So in this case, we could say, therefore, f of x is not differentiable at, at x is equal to 1. So that's how we check it. Now, you will have some problems like the ones that we saw before on continuity, where they'll say find the value so that this function is differentiable everywhere. Always keep in mind you have to be thinking about continuity first, and then second part of that is the left-hand derivative needs to be equal to the right-hand derivative. So here's an example of that type of a problem. Find all values of a and b such that f is differentiable at x is equal to 1. Well, let's just go through this one. So I'm going to go through the same two parts I did the last time. So if this is going to be continuous, when I plug 1 into that top rule for x, I would just get a, that needs to be equal to plugging 1 into the bottom rule, which would be, let's see, b times 1 squared would be b plus 1 plus 1, so b plus 2. So I got one equation with two unknowns. So the second equation we're going to use here to solve this out is actually going to come from the right and left-hand derivative piece of this. So if I were to look at f prime of x, what we would get if we did our one-sided or our piecewise derivative here is we would get a for the first rule for x less than or equal to 1. And then for the second rule, we would get 2bx plus 1, and that's for x greater than 1. Now, that's going to give me a second equation when I plug 1 in for x. So let's just write our system of equations here. For the continuity piece, I had a is equal to b plus 2. And then for the differentiability, or the right and left-hand derivative piece of it, I would have a has to be equal to 2b plus 1. And from that, what I can easily see here is that now I've got two equations, two unknowns, and when I solve that, I can see that a is going to be 3 when b is equal to 1. So I'm not going to go through the algebra here, but the main idea is you've got a 2 by 2 system. You can do substitution, you can do elimination, whatever you want. Probably substitution's the easiest here, but you'd end up with a being equal to 3 and b being equal to 1. So very simple to do, but the main idea is look at the continuity and then look at the right and left-hand derivatives. All right, so let's talk a little bit about calculators with derivatives. So you have to be very, very careful when you are evaluating derivatives on the calculator, because there's a few things that the calculator will do that might throw you off a little bit. The first is, this is actually derivative notation for the TI-83. And I'll show you the notation on the TI-84s in a second. I always leave that in my notes because there are some people that are still using TI-83s, and they have a little bit more syntax that they have to pay attention to when they're entering things on the calculator. But this is basically saying take the derivative of x cubed minus 4x, and then for x, we're going to substitute in -2 at that point. So when we do this on the calculator, what the calculator does, the calculator doesn't actually, the TI-84 and the TI-83 doesn't actually take the derivative and then substitute numbers in. What the calculator does is it does a really, really close approximation of what that derivative would be. So this is what the calculator does. In our case, we're evaluating at -2. So it would be plugging in -2 for A, and then it would be basically taking a point a little bit to the right of -2, a point a little bit to the left of -2, and then finding the slope between those 2 points. So it doesn't actually take the limit as h approaches 0. That's not what the calculator does. The calculator does this and says, okay, instead of taking the limit as h approaches 0, let's plug in a really, really small value for h, 0.001. And so, yes, it gives me a value that's very close to the derivative value, but it doesn't give me the exact same thing as what the derivative actually is. So you've got to be careful, because you're going to see problems where you're going to get an answer where, let's say the answer was 8. Well, instead of 8, the calculator is going to say 8.000001. And you have to realize that you're not getting the exact result because of the way the calculator is programmed to approximate the derivative. So be careful with that, and I'll show you what I mean by that here in just a minute. Okay, so another place where it can lead you wrong, and now that we've seen how the calculator does the derivative, now you can see how it can give you the wrong answer. So this next problem, I'm going to show you this on the calculator. This is saying let's take the derivative of the absolute value of x, and for x in that derivative, we're going to substitute in 0. So what I'm going to do here is I'm going to pull this up and I'm going to show you this on the calculator. So on the calculator, when you want to do a derivative, you can just hit math 8, and then I'm going to take the derivative of a function that's in terms of x. So I'm going to do dx, and my function is absolute value of x. So I'm going to hit alpha window to pull up the shortcut for absolute value. So absolute value of x, and we want to evaluate that at x is equal to 0. Now, knowing what the absolute value of x graph looks like, we know that this should be a value where the derivative doesn't exist, right? So we shouldn't be getting a slope for this because the left-hand derivative and the right-hand derivative don't match up. There's no tangent slope. There's no instantaneous rate of change at that point. It doesn't exist. So what the calculator gives you is 0. And the reason the calculator gives you 0, let me go back over to my notes here. The reason the calculator gives you 0 in that situation is because what the calculator is doing on that absolute value graph is it's taking a point a little bit to the right of 0 and a point a little bit to the left of 0, and it's finding the slope between those 2 points. That works 99.9% of the time. It's going to give us a good result. But when we have these special features like a corner or a cusp or a vertical tangent, the calculator is going to give us an incorrect result because of the way it's approximating the derivative. So it's not that the calculator is doing anything wrong. It's that the calculator is programmed to approximate the derivative as opposed to actually finding the derivative function and plugging a number into it. So you've got to be aware that the calculator can lead you wrong when you're looking at those derivatives. Okay, so we've also got another question here that I just want to show you. So this is the derivative of x cubed minus 4x. And we're going to look at that derivative that I mentioned earlier where we're going to take the derivative at -2. So I want to show you a couple of things on the calculator here. So on the calculator, let me go ahead and graph this function. So the function I'm going to graph is x cubed minus 4x. We're also going to graph the derivative of the function. So to graph the derivative, you can do the same thing on your calculator. You can hit math and then 8. That pulls up the derivative function. And I'm going to graph the derivative x cubed minus 4x. So I'm going to put in my x cubed minus 4x. That's one way to do it. The easier way to do this, rather than having to enter all of that notation again, is to actually just say, rather than entering the function that's already programmed in for y1, I'm just going to pull up y1. If I hit alpha and trace, that gives me a shortcut to these functions that I've programmed into the calculator. The one that I've programmed in is y1, so I'm going to select y1. So now it's telling the calculator, take the derivative of y1. We're going to evaluate this right now for all values of x. And what that's going to do is, rather than finding the derivative at a single point, it's going to graph the derivative for all values of x. And it doesn't actually find all values of x, but it finds a bunch of individual points and then connects them together to create what appears to be a smooth curve. Okay, so when I graph this, I have the original function already there, and then you can see the red function that went through there is the derivative. And it makes sense because I had a cubic function to start with, and I got a quadratic to end with. Now, what I want to do is I want to look at what's the derivative value at -2. Well, if I trace, and when I hit trace, it's going to default to y1. I'm going to hit the down arrow, so that's going to select the y2 function. And then I'm just going to put in -2. Let's trace to -2 and see what the calculator is telling me the derivative is. Notice the derivative here, 8.000001. So it's giving me a very, very close approximation of the derivative, but it's not giving me the actual derivative value. So again, keep in mind what the calculator does when it does those derivatives. When it calculates those derivatives, what it actually does is what I showed you right here. It takes these points that are very, very close together using this h value of 0.001. So that's why we're getting a number that's not quite exactly what the derivative is. We have to understand when we look at the calculator that, oh, well, that means it's exactly -8 because it gave me such a close approximation to -8. All right, so the last thing I have for you here is what we call the intermediate value theorem for derivatives. And this really isn't any different than what we had before. But I just wanted to show you that that same logic we had for the intermediate value theorem can apply when we're looking at derivative values as well. So it says if A and B are any 2 points in an interval on which f is differentiable, then f prime takes on every value between f prime of A and f prime of B. That's the exact same statement as the intermediate value theorem, except we're talking about f prime instead of f. Okay, so with that being the case, here's the type of question where that's going to become important. It says in this problem at the bottom, if f of x is a differentiable function for all values of x, what is the minimum number of points where f prime of x is equal to 0? Okay, so we know that f of x is a differentiable function. So that tells me the derivative has to exist for all values of x. I'm not going to skip over any points in my derivative function. That means my derivative function is continuous. So knowing that my derivative function is continuous, what's the minimum number of times I crossed over 0? Well, now think about the statements that you wrote, and you had one of them on the test where you had to write a statement justifying why there was at least 1 0 on an interval. Well, we're going to do the same thing now. I'm not going to write out the whole statement, but I'm just going to go through the reasoning for it. So look between x is 0 and x is 2. We went from a negative to a positive. So on that interval, we had to cross over 0 at least one time. Over here from x is 6 to x is 8, I went from a positive y value or a positive f prime value to a negative f prime value. So again, we had to cross over 0 there because we know f prime is continuous. And then from 8 to 10, you can see that we went from a negative f prime to a positive f prime. So what's the minimum number of times that we would have to cross over 0, or what's the minimum number of times that f prime of x would be 0? It would be at least 3 times, or 3 points, I should say. Okay, so it could be more. We don't really know what's happening in between all of these values, but we do know that this is a continuous function, and we can see how many times we've definitely changed from negative to positive and positive to negative. So that's the idea behind those types of questions, and that's where the intermediate value theorem starts to get used a lot. If we had to justify this, if you had to write out a statement justifying it, it would be just like we did before with the intermediate value theorem. We would have to say, since this function is differentiable for all values of x, there must be at least 3 points where the derivative is equal to 0, because the derivative went from negative to positive or positive to negative at least 3 times. Okay, so that's really all you're looking for on a problem like that. Primarily, we're going to use it just for the reasoning to figure out the number of points. But if you did have to justify, it's just like justifying with the intermediate value theorem that we saw before.